One of the absolute greatest things about the sum formulas for the trig functions is that they allow you to very easily derive the double angle identities. Double angle meaning we're doubling the angle in the argument, right? We're not finding the sine of theta, we're finding the sine of 2 theta, or the cosine of 2 theta, or the tangent of 2 theta. So we're doubling that angle. And it's very easy to derive these formulas if you just remember that 2 theta is the same thing as theta plus theta, right? So we'll call alpha theta, we'll call beta theta, and we're just going to use that sum formula for sine that says take the sine of the first angle times the cosine of the second angle, which happens to be the same as the first angle. Sine has the same sign, and then we do the cosine of the first angle times the sine of the second angle. But again, these guys are the same thing, right? This term right here is exactly the same as this term right here. It's just one cosine of theta and one sine of theta being multiplied together. So that's 2 of them. 2 sine of theta, cosine theta. Very, very quick derivation. So if you know the sum formulas, then you know the double angle formulas. Same thing with the cosine of 2 theta. All you've got to do is apply the formula, right? Cosine of theta times the cosine of that second theta, and then cosine flips the sine, and then sine of the first theta times the sine of the second theta. Now this is going to get a little bit more complicated because we like to think about our favorite identity. So one way we can write this is cosine squared of theta minus sine squared of theta. Nothing wrong with that. But remember, of course you remember this because this is your favorite identity, that the cosine squared of theta plus the sine squared of theta equals 1, which means I can replace the cosine squared of theta with 1 minus sine squared of theta. If I do that, then if I replace cosine squared of theta with 1 minus sine squared of theta, I've got a minus sine squared of theta minus another sine squared of theta. So I'm minusing and subtracting 2 sine squareds of theta. Okay, so that's an alternate version of the double angle identity. We really need to be familiar with all 3 of them. Wait, what? There are 3? Yes, there are 3. I've got 1, I've got 2, I've got a third one here. So this one uses cosines and sines. This one uses just sines. So what do you suppose the last one's only going to use? That's right, it's only going to use cosines. So if we want to get rid of the sine, we have to replace it with something else. So remember that 1 minus cosine squared of theta is the same thing as the sine squared of theta. We know that because that's our favorite identity in disguise. So if I take cosine squared of theta minus sine squared of theta, but that's 1 minus cosine squared of theta, that's just this line right here, replacing the sine squared theta with something that sine squared equals. Then I realize, oh, I'm subtracting a 1, but I'm also subtracting a negative cosine squared of theta. Subtracting a negative is adding, so it's cosine squared of theta plus cosine squared of theta, or 2 cosine squared of theta minus 1. So we like to use all 3 of these. They're useful in different scenarios, so you're going to want to be familiar with all of those. Finally, we've got the tangent of theta, tangent of 2 theta, and that one is going to work more like the sine. There's only one version of it. Remember that the sum formula for tan says tan plus tan on the top, and 1 minus tan tan on the bottom. So on the top we're adding the 2 tangents together. On the bottom we're multiplying the 2 tangents together. So in the numerator we get 2 times the tangent of theta. And on the denominator we get 1 minus tangent squared of theta. Okay, so those are your identities. It takes only a few minutes to derive them if you know the sum identities. So that's all there is to it. And hey, look, they're all right there. So that's all well and good. So what do we do with them? Well, the same thing we do with all of our identities. We just kind of play around with them and replace things. If I know that the sine of theta is 3/4, and I'm interested in finding the sine of 2 theta, please do not say, oh, I'm just going to double the 3/4. That's pretty important concept, and we should know that. If we double 3/4, we're going to get an answer bigger than 1, and that's just not possible for an output for a sine function. So we know that's not true. So how do we do it? Well, of course, the answer is that we're going to use the double angle identity, right? We know that the sine of 2 theta, we just figured it out, is 2 times the sine of 1 theta times the cosine of 1 theta. So all we have to do is figure out what the sine of theta is and the cosine of theta. Oh, we've been doing that for months, right? If I know that the sine of theta is 3/4 and it's in quadrant 1, then I'll just build myself a triangle. And theta is right here. The sine of theta is 3/4. So this missing side down here is not 5. It's not a 3, 4, 5 right triangle because the hypotenuse isn't 5. The hypotenuse is 4. The horizontal leg here is square root of 16 minus 9, 4 squared minus 3 squared, which is 7. Square root of 7. So that's obviously helpful because that's what I need to use to find the sine and the cosine. Well, actually, I already know that the sine of theta is 3/4. That was given. But now I can use the triangle to figure out that the cosine of theta is root 7/4. And that's your answer. You're just going to have to simplify it. So 2/4 reduces, so the 2 is gone, and we have 3/2 times root 7/4. And 2 times 4 is 8. So 3 root 7. Again, just like on those in the last section, we're not actually solving for theta. If we did, we'd need a calculator. And this is a non-calculator problem. And also the calculator wouldn't give you the exact answer with a square root. It would give you a decimal. And that's no fun. We don't like that. We like exact answers. So yeah, this is a good way to use the double angle identities. For the cosine of 2 theta, we can use any one of the 3 that we like. I'm going to use the second one, the one that uses sine, because, well, first of all, because why not? Second of all, the reason is because that was given. So I feel like that's the safest one to use. It's possible that I subtracted wrong or something, and I got the wrong value down here with the square root of 7. I know that this is right because it was given to me, so I'm going to try to use that one. And then it's really quick. We just do 1 minus 2 times 3/4 squared. Well, we know that 3/4 squared is 9/16 times 2 is going to be 9/8. And then we're going to get 8/8 minus 9/8, which is 1/8. You might find it a little surprising that we had square roots in one of our answers, but not in the other. Thought I was selecting that. But that's definitely possible. So don't worry about it too much. One thing you could ask yourself, does this make sense? Well, remember that sine squared of an angle plus the cosine squared of that same angle should equal 1. So you could really look at these two fractions and square them both and realize that when you add them up, you'll get 1. That's a worthwhile activity for you to give it a try. But I'm going to go ahead and move on to that last part, which is tangent of 2 theta. And I'm going to go ahead and do this using the identity, the double angle identity, tan of 2 theta equals 2 tan of theta divided by 1 minus tan squared of theta. So looking at our triangle, the tangent of theta is 3/7. So I'm going to have 2 times 3/7. I'm going to divide that by 1 minus 3/7 squared, which isn't so bad, right? We got 6/7 in the numerator. And in the denominator, we get, 3/7 squared is 9/7. So this is 1 minus 9/7. 1 minus 9/7. But 1 minus 9/7 is just negative 2/7. And then we'll still have our numerator of 6/7. So when we multiply by the reciprocal, we're dividing by negative 2/7, so we can multiply by negative 7/2 or 7/2, right? So times negative 7/2. So the answer will be negative. The 6/2 reduces to a 3, and the 7/7 should reduce down to a root 7. So that would be your tangent of 2 theta. Now, a nice double check here, you should be able to see that when we take sine divided by cosine, you get tangent. And I'm noticing now that we don't, And that's not because this answer over here is wrong. It's because I made a mistake earlier on that I just caught as I was working this out. So use your answers amongst themselves, right? You know how they're supposed to be related, so you can figure out whether your answers make sense. And I made my mistake right here, right? 8 minus 9 isn't 1, it's negative 1. So the cosine of 2 theta is negative. And that makes sense if this angle is bigger than pi over 4, which apparently it is. When we double the angle, it's going to be past pi over 2. We're looking at a quadrant 2 angle. Okay? The quadrant 1 angle doubled may stay in quadrant 1, or it might double out to be in quadrant 2. And apparently in this case it does go into quadrant 2. And we can see that because we have a positive sine value, but a negative cosine value and a negative tangent value.